Hello everyone, my name is Ali Behnood and I am an assistant professor in the Department of Civil Engineering at the University of Mississippi. Today I will be presenting on the topic of Metaheuristic optimization based ensemble learners for the carbonation assessment of recycled aggregate concrete. So the content of my presentation will be as follows. I will begin with an introduction to the carbonation of concrete and discuss the concept of carbonation depths. Following that, I will provide a detailed description of the data and the feature selection process utilized in this study. Next, I will delve into the research methodology employed, which will be followed by an explanation of the model development. Finally, I will present the results and key outcomes of the study. Carbonation of concrete is a chemical process that occurs when carbon dioxide from the air penetrates the concrete surface and reacts with calcium hydroxide present in the concrete. This reaction produces calcium carbonate. In other words, the process begins with the diffusion of CO2 into the concrete, where it encounters calcium hydroxide and forms calcium carbonate and water. The depth to which carbonation penetrates the concrete is referred to as the carbonation depth. This depth is influenced by several factors, including the concrete's porosity, moisture content, and the surrounding CO2 concentration. Carbonation reduces concrete's pH from around 13 to below 9, compromising the protective oxide layer around steel reinforcement and leading to potential corrosion. This corrosion can cause structural damage as the expanding steel cracks and spalls the concrete, increasing maintenance costs and reducing the concrete's service life. Mitigating carbonation in concrete involves improving the mix design by reducing the water-to-cement ratio and adding supplementary cementitious material to enhance density and slow carbonation, ensuring adequate concrete cover and using high-quality concrete for the cover delays carbonation from reaching steel reinforcement. Proper curing practices, surface treatments, and regular maintenance also play crucial roles in reducing CO2 penetration and addressing early signs of carbonation and corrosion. Recycled aggregate concrete affects the carbonation process of concrete primarily due to its increased porosity, higher permeability, and altered microstructure compared to natural aggregate concrete. These characteristics allow carbon dioxide to penetrate more easily, accelerating the carbonation rate. The weaker interfacial transition zone in recycled aggregate concrete also contributes to greater carbonation depths. Additionally, recycled aggregate concrete's reduced alkalinity diminishes its ability to protect steel reinforcement from corrosion. To mitigate these effects, as discussed, a wide range of preventive measures can be taken. While recycled aggregate offers sustainability benefits, its higher susceptibility to carbonation necessitates these preventive measures to ensure durability. Some supplementary cementitious materials such as fly ash can reduce the carbonation resistance of concrete, primarily due to their lower calcium hydroxide content compared to ordinary Portland cement. This lower calcium hydroxide content leads to a reduced pH level in the concrete, making it more susceptible to carbonation. However, the use can be optimized to balance this effect by improving overall durability. Some other supplementary cementitious materials such as silica fume can enhance carbonation resistance by refining the pore structure and increasing the density of the concrete. The contributions of this study are manifold. We pioneered the application of XGBoost coupled with novel metaheuristic optimizers to model carbonation depths in recycled aggregate concrete. Through rigorous evaluation, including sensitivity analysis and complexity comparison, we demonstrate the superior accuracy and efficiency of the proposed models in predicting carbonation depths. This study also provides a comprehensive shape analysis, offering deep insights into the factors influencing carbonation depths, a perspective not thoroughly examined in existing literature. The development of a user-friendly graphical user interface for our model significantly enhances its practical utility, enabling professionals to predict carbonation depths with ease, thereby facilitating more sustainable construction practices. An extensive database is required to develop a reliable carbonation depth model for recycled aggregate concrete. For this purpose, a comprehensive database of the carbonation depths of recycled aggregate concrete was gathered from the published peer-reviewed journal and conference papers. The data used in this study can be classified into three different groups. The first group of data is the information on mix design, such as the quantities of cement, fly ash, water, natural coarse aggregate, recycled coarse aggregate, and natural fine aggregate, as well as the recycled aggregate water absorption. The second information is on the compressive strength of recycled aggregate concrete at 28 days, and the third group of data records is on the information about test factors such as CO2 concentration, exposure time, temperature, and relative humidity. The multicollinearity of input features is an important concept that can decrease the interpretation power of the developed machine learning model. To find highly correlated input features, the correlation coefficient and variance inflation factor of the JIS input feature are usually used to check the multicollinearity of input features in regression problems. As illustrated in the first figure at the top, the VIF values of temperature and relative humidity are very high, and these features are ignored in this study. To prevent multicollinearity, water-to-binder ratio, fly ash to binder ratio, recycled aggregate ratio, recycled aggregate water absorption, compressive strength, CO2 concentration, and exposure time were chosen as the final input features. The VIF values of the final input features are given in the second figure at the bottom. After preparing and cleaning the database and selecting features, different steps have been taken to model the carbonation depths of recycled aggregate. The first step is to select appropriate optimization algorithms to find the best hyperparameters for the XGBoost algorithm in modeling the carbonation depths of recycled aggregate concrete. XGBoost technique is an extension of the gradient boosting technique, which benefits from advanced regularization and can enhance the generalization capability of the developed model. As an ensemble boosting method, this technique generates several weak estimators successively to reduce the prediction error. In this study, three synthesized ensemble algorithms are introduced in which three newly proposed metaheuristic optimization algorithms are used for tuning the hyperparameters of the XGBoost technique. Reptile search algorithm and Aquila optimizer are two inspired by nature optimization algorithms in which the hunting strategies of crocodiles and Aquila respectively are modeled to solve optimization problems. In the case of arithmetic optimization algorithm, the distribution behavior of four main arithmetic operators including summation, subtraction, multiplication, and division are used to solve optimization problems. To develop the synthesized XGBoost models for predicting the carbonation depths of recycled aggregate concrete, the gathered database was divided randomly into developing and testing data sets. In the developing phase, the k-fold cross-validation technique was employed in which the developing dataset was randomly partitioned into k-folds with almost equal. To examine the developed XGBoost model, several error measures were used in this research, consisting of root mean squared error, mean absolute error, mean absolute percentage error, coefficient of determination, and a scatter index. After coding and running three synthesized XGBoost algorithms in Python, their performance over 20 independent runs, considering population sizes of 30, 50, and 70 during the validating phase for 200 iterations was analyzed. The results, including the mean RMSEs, best RMSEs, and the standard deviations of these algorithms are shown in this figure. It can be seen that generally the XGBoost Aquila optimizer algorithm outperforms the other two algorithms in terms of mean and best RMSEs, with the XGBoost reptile search algorithm ranking second. The error measures of the best synthesized XGBoost models for the validating and testing phases are given in this figure. Generally, the best XGBoost Aquila optimizer model has the best rank, and the XGBoost reptile search algorithm and XGBoost arithmetic optimization algorithm models are in the second and third orders for both phases, respectively. This figure illustrates the error bar plot of the proposed models. In general, there is a decent balance between positive and negative prediction errors, inferring that the developed models do not underestimate or overestimate the carbonation depths of recycled aggregate. This figure illustrates the impact intensity of the selected input features on the carbonation depths of recycled aggregate concrete, as well as their positive or negative influences. In total, environmental factors affect the carbonation depths more critically than recycled aggregate concrete mix design factors. The exposure time, with the mean absolute shaft value of 4.3, has the first rank, which is a 42% mean absolute shaft value difference compared to CO2 concentration. The compressor strength and water to binder ratio with the mean absolute shaft values of 2.46 and 1.81 are in the third and fourth ranks. Recycled aggregate water absorption has a trivial mean absolute shaft difference with the fly ash to binder ratio and is ranked fifth. Among the 7 input features defined in this study, the recycled aggregate ratio has the lowest rank. The partial dependence plot visualizes the average global dependency between the developed machine learning function and one or two input features of interest considering their marginal effects. This plot depicts the relationship complexity between the output and input features of the defined system. The one-way parametric study of the input features is depicted in this figure. There is a general increasing trend in the carbonation depths with an increase in the water-to-binder ratio and the reduction in compressive strength value. Because of the interaction between input features, a two-way parametric study was conducted to gain better insight into the concurrent effects of two input features on the carbonation depths of recycled aggregate concrete. The two-dimensional partial dependence plots of several pairs of the input features are illustrated in this figure. For example, the simultaneous increase of recycled aggregate ratio and recycled aggregate water absorption results in a higher carbonation depth of recycled aggregate concrete. Several other observations can be seen in this figure about the concurrent effects of two input features. To use the developed synthesized XGBoost models in practical applications, a user-friendly graphical user interface was designed in which the crucial input features defined in this study are used to obtain two types of outputs. First, the singleton prediction estimates the carbonation depths of recycled aggregate concrete within a specific exposure time. Second, the diagram prediction predicts the carbonation depths of recycled aggregate concrete over different exposure times. With that, I extend my gratitude to my colleagues whose invaluable contributions have greatly facilitated the execution of this study. Dr. Golabshani at University of New South Wales, Dr. Kim again at University of New South Wales, Dr. Tuanengio, University of Melbourne, and Dr. Karshani at University of New South Wales. Thank you very much for your attention. Please feel free to reach out if you have any questions.